So what we're so the underlying gadget here, the underlying thing we're talking about is phase space. And I'll always write it as an M, and then it's so, and for us it's always going to be an even dimensional space, and it's going to be the so it's going to be the space with coordinates. It's QJ and PJ, where J is from 1 to D. Okay, just a second. Right there. Okay, and so now the crucial kind of extra structure than just being a vector space that you have in here. So you don't have an inner product or anything, but you do have this extra structure, which is that the Poisson brackets, QJ, QK, so that the Q's plus so-called Poisson commute with each other, so do the P's. But you have a non-trivial relation between the P's and Q's, and that's delta. And so you should think of this as more as kind of an interesting variant on an inner product. So what you should think of is so the QJ and PJ are a basis. So these are linear functions on M, and they're actually a basis for the linear functions on M. Every linear function is a linear combination of these things. And you should think of these relations as giving you something that's like so these are kind of an analog of an orthonormal basis if you had an inner product. These are things which they have, instead of having a symmetric inner product, there's an anti-symmetric bilinear form here. So there's an anti-symmetric bilinear non-degenerate form on M star, which on the basis vectors for the dual behave like this. And so you should think of these as being kind of the analogs in this new kind of geometry of where you have an anti-symmetric bilinear product of in the usual inner product, just the relations that say that you have an orthonormal basis. So this is the kind of symplectic analog of an orthonormal basis. Okay, and in particular these well. Okay, maybe that's probably what I was saying about this. Okay, now here's where things get tricky. So the simple calculations that I really want to emphasize, and what we're actually going to need when we quantize, all rely upon this M star on this dual space. So but the problem is that what you naturally, in some sense, the natural underlying geometrical, so the underlying geometric space is this is M, not M dual really, and this M actually generalizes to what do I want to say about this? Okay. Oh, actually, let me just say this. So no, you can use the well. What these guys give you, sorry, some star and the Poisson bracket just restricted. So instead of feeding this thing arbitrary functions, if you just feed it linear functions, this gives you this gives you this anti-symmetric bilinear form on there, and I'll often call that omega. And this is what I meant. This is so it's this guy that's the analog of the inner product in this case. Okay. And the values of this guy are determined by these relations. Okay. Now so omega, just like In the Euclidean case, the inner product gives an isomorphism V. Okay, so whenever you have a vector space, if you have an inner product on it, you can use the inner product to get an isomorphism between the vectors and its dual and the dual. That to a vector in here, you just put the vector in here, and that gives you a linear map on whatever you put in the second thing. And so this is the thing that happens when you have inner products, these symmetric non-degenerate bilinear forms. That the V, sorry. But you can do the same thing. Can do the same here. Here with omega. And so that then what you have is that so omega, so if V, I don't want this, yeah, okay, and you can get an isomorphism M. And I think I'm not going to. Okay. Let me not actually. So I explained this in some detail in the text, but let me not really say anything more about this, other than this is kind of why the geometry here is kind of fairly tricky. It's that you want to be able to. You end up in the geometry wanting to work with things on M, but you've actually got the only gadget you have. You really want to talk about these P's and Q's and use this gadget, so you're actually on here, and you have to move back and forth, just like you would in the Euclidean geometry between V and its dual, but here between the phase space and the dual phase space. And if you look at anyway, this leads to kind of various ugliness and confusion at various points that you have to anyway. You have to kind of choose this isomorphism using this guy at some point. And also here, this is symmetric, so it doesn't matter which order you stick the V in here. In here, if you do it, there's going to be a sign depending upon which order you do it.
But do you have an isomorphism for infinite dimensional space?
Yeah, well, I mean, in that case, you'd have to be much more careful. Yeah, I'm assuming so these spaces, I'm assuming, are all finite dimensional. If they were in the case where they're infinite dimensional, and this happens later on, so the phase spaces we're talking about now in quantum mechanics are all finite dimensional. When you get to quantum field theory and you're looking at then you actually have infinite dimensional phase spaces, and then you have to be very careful about exactly what. But again, then it's a typical problem. What kind of functions are you talking about? It's a function space or a space of distributions or something, and you have to worry about that. But yeah, this is all finite dimensional. Okay. But now, so anyway, so this is just kind of I'm kind of trying to explain kind of one reason why. Working with the geometry is tricky is because you're going to have to do this, and you're going to have to use this guy, and he's going to introduce some confusing things to keep track of. But the reason for doing this, let me just say that I wanted to one reason I wanted to talk about the geometry is that this whole story that I'm going to tell you actually goes through in much more generality. So everything we do, we'll do. Well, actually, I shouldn't say everything, but everything we'll do for most of this lecture, whenever I'm talking about the geometry, works for M, a manifold. Okay. Locally, and then locally. So, I mean, if you haven't studied geometry, what manifolds are, manifold you should think of as being something which just you've built it by taking up several copies of RD, or in this case R2D, and which are locally like R2D. So maybe the thing to think of is maybe something like a sphere where you've put some kind of two-dimensional charts on the top hemisphere and on the separate one on the bottom hemisphere, and everywhere it locally looks like R2, but but globally there's a more complicated geometry going on. Well, the point is you can do the same thing here, and then what we're going to do is so I'm trying to just kind of say things in a way which is quite concrete on R2D, but also easily carries over if you think of you just have this R2D locally, and if you study geometry, you should see how it's going to carry over to a general manifold. But in general here, so it's the same idea. So one idea is that. So this is an idea from geometry is locally. Okay, at m is an element of m. If you're at some point and it locally looks like R2D, then what you want to do at some point m, you want to ask what are the tangent vectors? What are the if you're on R2D, you just want to know kind of what's the basis of the vector space. What's the basis of the vector space? Or if you locally look like R2D, you're just what's the basis of R2D at this point? And so the standard. So one standard way in geometry of thinking of what it means to pick a to pick a basis of this tangent space or of this local space is you have basis vectors. And so what you can do is you can think of you can define vectors by in terms of derivatives, that you can imagine that if you're moving in this direction, if you want to know how a function is changing in this direction, it's infinitesimally changing by taking the derivative. So what you do is you take as your basis vectors d qj and d pj. Okay. So just as when I was talking about this dual space, as saying that the basis vectors of it are the qj's and the pj's. Well, if you wanted to know, what are the basis vectors of M, not of M dual, and what you really know about M is that it has these q and p coordinates. Then it's one way of thinking about a basis of the vectors at any given point is in terms of these derivatives. And so this now I'll say more about this and I'll use this, but this is kind of confusing. If you haven't studied geometry before, this kind of thinking of identifying vectors with derivatives is kind of a confusing thing to do. And so this is there's several reasons why I think this chapter 15 trying to do this was a little bit misguided. The first reason was that there's that confusing isomorphism involving omega. The second reason is that if you haven't thought about things this way, it's confusing here. But it is worth spending some time trying to see if you can make sense of this if you haven't seen it before. Okay, so but that's that. Then so instead of omega so instead of what we had on this dual space, okay, and then maybe the important thing to say about this whole story is that for many cases in which you can do all this, you can take M. You actually can take M, for instance, to be a sphere. M as a sphere is a perfectly good example of a generalized phase space where it's a manifold, not a vector space. But then, if M is anything other than R2D, then there really is no M star. There is no dual space. There's no dual space to a sphere. It's just so in general, if you what I'm trying to say for a while here works in general, and in general you actually don't have this and you don't have this. But the information that corresponds to the Poisson bracket is that you have a and so this is something that you have what's called a symplectic form. And and one way of writing it is P and then dp dqi qj tensor e. Now these guys are what these guys are is so I've changed to a standard notation of geometers. So for geometers, what's true is that you globally don't have this, but locally at any point on M, if your tangent vectors are given by this, you can look for the dual. The duals of these guys, the things that are dual to these guys, the things that if you put this together with this, you'll get delta JK, and so this is the analog. This is just QJ, but locally. And same thing. This is just PJ. So this notation of putting a D in front of these means that you're just kind of working on the tangent space. You're working, and these are called differentials. But you should think about it that really all this is just this locally. This is just saying that you want to construct a bilinear form in this way out of the basis vectors Pj and Qj. So I don't want to go more into this because this is something. So this is if you study differential forms, this is something called an antisymmetric. Well, this is a different. Well, anyway, this is now what's called an antisymmetric two form, and there's a whole long story in Song and Dance about how to work with these things. But it
the same as the Taylor form.
Wait, what?
This guy is the same as Taylor form.
As the which form?
The Taylor form.
Okay. Sorry, what's the word you're saying? Which kind of form?
Maybe it feels like KHLER, maybe like that.
Sorry, I can't. How's it spelled?
Like KAHLER.
Oh, Taylor. Okay. Yeah, you're asking again. It says Taylor. Okay. Okay. Yeah. So this is something that's called a Anyway, it's the symplectic two form. And it is this guy. Okay, so what you're asking about it is again something much more subtle. So one thing, okay, maybe just to say some very general things about this. That in geometry, when we study geometry, mostly what we talk about is Romanian geometry, and this is what also physicists study. It's what you use in general relativity, and it involves curved spaces where locally you have a local version of the inner product. That's the metric. Okay. Now, if you take a more advanced course of geometry from mathematicians, and physicists rarely actually get to this, but then the idea is that instead of thinking about a local symmetric two form, you can think about a local anti-symmetric two form, like this case. And so what I'm telling you about is what a mathematician would say is the subject of symplectic geometry. So symplectic geometry, what it means is you've locally got these coordinates, you've locally got this basis for your tangent space, and you've got a which in local coordinates you've got this anti-symmetric bilinear form, which called this guy. Now the crucial thing about this that makes all this interesting is something more subtle, which is that if you have anti-symmetric two forms, there's something called the Theorem differential you can do to them, and this satisfies the omega is equal to 0. So and this condition corresponds to the Jacobi identity. Okay, so when people talk about symplectic geometry, what they're doing something which is very much like what we've been doing with Poisson brackets, except they're doing it in a way which works on curved manifolds. And the analog of the Poisson bracket is this guy, and the analog of and it's anti-symmetric, just like a Poisson bracket. And the analog of it, the fact that it satisfies a Jacobi identity, is that the form satisfies this. But I can't explain to you what this D operator is. This D operator takes anti-symmetric two forms, anti-symmetric three forms, and you get the 0 form, and that's Jacobi's identity. Okay, so this is the whole story of symplectic geometry. Now, if you want to get even more tricky and more advanced, maybe it was what you heard about, is you can ask, what if, so a complex manifold. So what if you're doing geometry and so a complex manifold, let's say complex manifold is locally looks like this becomes CD. Okay. So in a complex manifold, instead of having a bunch of real coordinates, you have some coordinates that are complex numbers. Okay. Now, if you have a complex manifold, that's also then you can ask, well, it's got to be even dimensional because complex numbers are always come in pairs of real numbers. So as a real manifold, it's even dimensional. And then so you can do Romanian geometry, and you can do symplectic geometry. And so you have this metric, which is the symmetric thing, and you have this anti-symmetric thing, the symplectic form. And the Kähler case is when they're in a certain sense that they're compatible. So Kähler so this is anyway, yeah. So this can be a Kähler form, but in a very in a much more sophisticated context, when you're dealing with a complex manifold with a metric which is compatible with this in the correct way, then you say you have a Kähler manifold, and this is the Kähler form. Okay, sorry, that was very long-winded, but I thought it might be a good idea to kind of so this puts all this in the context of much of the whole range of different kinds of geometry that mathematicians talk about. But we're not going to letting your coordinates be complex is leads to all sorts of exciting things which we don't want to get into. This isn't so. All of our coordinates are always going to be real. Okay, and maybe let me just say, is that yeah? So this is all. So are there any other questions about kind of what this has to do with the general ideas about geometry? If it's something, because I'm going to go back to get to saying much more concrete things. I'm going to go back to R2D right now. After this was about as far as I want to go into general geometry. Okay, but just the claim, the motivation for saying this in this general form is we'll see everything that all the things that I'm doing now, which I'm going to do on R2D, they're all set up so that these local calculations fit together on an arbitrary manifold to give the same things that I'm saying are true on R2D are going to be true on arbitrary symplectic manifolds. Okay, so let's go on to now. So back to much more concrete. So. Okay, so the next thing you want to think about is our vector field. And so what a vector field? So if you've got a space, and you might take it to be R2D. So far we've been talking about functions on the space. And I've also kind of claimed that at a point you can take a basis. If you have coordinates, you can take a basis of derivatives with respect to the coordinates and get a basis of a local basis at that point. But what a vector field is going to be instead of for each point you're a function and you have a number. It's for each point for each m. Element of m, you get a vector. Okay. And so very explicitly, so we're gonna, when I write x here, I'll often mean a vector field. But what this is going to be is it's going to be, so if we're using our coordinates to locally give us basis vectors, d, dq. Actually, I guess I should write it down. Well, let me actually just do this. I'll write the formulas for d is equal to 1, and then it's pretty easy to see how they generalize. And then you've also got so this is one basis element of the vectors at a point. The other one is this guy. So what you do is you take some function of where you are, and I'll call it f sub q, and then so you let the amount of this vector vary as you move around on M, and then you let the amount of this guy vary. So it's f p q. And the picture is something that we actually see even in our kind of in our calculus sequence. You often think about this is really what it is that at each point you've chosen a vector, and this vector has components. I mean, if this is q and this is p, then this has a certain component in the. This guy measures your component in this direction. This guy measures your component in this direction, and the point is that you have one of these everywhere. So you have anyway. So this is what the picture you should have in mind for a vector field. It's just that for every point in, and this is going to be our space M. And this is the two-dimensional case. For every point, it's a vector, and in the and so it's just but there's a vector at every point with component of coordinate and components given by these two functions. Okay, now so there's a lot more about this in the book you can do, but I want to let me just kind of start saying some very general things about this. So these form, so vector fields form a Lie algebra. And again, okay, and this and again, so because taking with bracket. x sub x1, x2 is just x1, x2 minus x2. So now it just, okay. So if you get it, the way this subject works is that if you've got some kind of vector field, and you take and what you do is you act with the second vector field first on functions, then act with the first vector field, and then subtract what happens if you do the opposite. Well, what happens is, in general, you get what happened is that the mixed partial derivatives are going to cancel, and so what you end up with is you end up with that this guy is also a vector field. And you can compute these things and find out what the anyway, and you can see what you get if you actually just start computing. You can get a formula for this guy and see what he is, and you'll see that he's a vector field. Okay, and then so this is again this is an example of an infinite dimensional. So very often you often talk about vector fields in geometry or in various applications, but you don't necessarily think of them as a Lie algebra, just purely because they're infinite dimensional. So you have all these questions about exactly which vector fields are you talking about? Are things going to converge? And there's a lot if you do anyway. The minute you get outside this the finite dimensional Lie algebras and start working with infinite dimensional Lie algebras, things get much more complicated. So you don't necessarily always want to do that. But this is certainly what we're going to. But for the geometry that we want to do, this is what's important. What's important is that we've got our phase space. If you look at the vector fields on our phase space, they form a Lie algebra, and this Lie algebra. And this comes with a representation on functions on it. Okay. So these vector fields act on functions, and so this is a Lie algebra, and you're explicitly kind of given it as represented on functions on it. Now, the thing this, from the point of view of representation theory, though, this is a very, very difficult thing to analyze because the representation is infinite dimensional, the Lie algebra is infinite dimensional, and if you play around with this for a minute, you'll see that this is definitely not an irreducible representation. So the thing that you would like to do, which is given an arbitrary representation, break it down into irreducibles, is extremely tricky in this situation. You kind of can't get very far because of the infinite dimensionality and the fact that this is actually a highly reducible representation. You don't want to anyway. So that doesn't lead to any particularly nice theory, but it is a Lie algebra with a representation. So in that sense, you've heard about it before. Okay, and so you can ask what if somebody gives you a Lie algebra, you can ask what's the corresponding group. So the group next thing I want to say about it is this group and is given by so the corresponding group has elements also acts. So let me just say this: it's the group that acts on M. So an M by taking a point by X on M with a group element e to the t x. So if you have a Lie algebra element, what you want to do to construct the groups, you want to be able to exponentiate the Lie algebra element. Now your problem is that these are not matrix groups. You can't just exponentiate, but you have to define what is the thing that's going to correspond to exponentiating the algebra elements and getting a group, and it's going to be the group element. It takes M to it's going to take M to itself and takes M to M by to the point you get by flowing along on X for time t. Okay, so I mean, I can write down various formulas about this, but it's maybe better to think about this. And what happens if somebody gives you a vector field? One thing that you can always try to do with your vector field is what's called integrate the vector field. In other words, you want to find some kind of you want to find some kind of curve that's given by such that these guys are give you the tangents. So the flowing means find a curve that, as it goes through each point, the tangent to the curve is given by the vector field. Okay, so if you just take those words and say, find a curve going through M as a function of t, and that at time t, at a point M, the tangent to the curve is given by the vector field. Okay, take those words, you can write them out as a differential equation, and then the idea is you solve that differential equation, and if you want to know what the group element is that corresponds to exponentiating a vector field, well, it's the group element that takes each point in the manifold. Let's say this was at t is equal to 0, and it flows along for some time t. Okay, so sorry, this is kind of a fairly, again, this is a fairly large package of information about differential geometry, about geometry. But it really, in some sense, it's quite. You can make this very concrete because everything is just in the, in R2D, and these are just simple first order. It's a simple first order differential equation you get in terms of the vector field, and you can think about its solutions, and you can do all this. I mean, the new piece of a thing I want to say about this is just that there's an underlying group here, and there's an underlying Lie algebra here. Whenever you're dealing with a vector field, the problem is that they're infinite dimensional. It's an infinite dimensional Lie algebra. It's an infinite dimensional group. There's kind of extra problems that occur with a group that you don't actually. You have to worry about. That you have to worry about existence and uniqueness of the solutions to your differential equation. Your solution may go off to infinity at some finite t, or hit some singularity, or do something, and so you might, whether you really have you may not actually have the kind of group that you thought you had. Okay. So anyway, so this is again just kind of I'm starting out with something very, very concrete, which is these guys, and then in principle, all of this can be made very concrete. It's just about, this is just this guy. You can work out what this guy is in general, and this story really just is based you just have to write down in equations what the equation is for these flow lines. So for these lines you're going to flow along, and then you can figure out what everything I'm saying here. So this is relatively concrete, but it is a package of information that's a little bit hard to get used to. So I didn't want to. That's one reason I didn't want to emphasize it too much. Okay. But this is true for arbitrary manifolds. Now, if we're on a symplectic manifold, now this is where things get interesting. That there's two Lie algebras. Now there's two infinite-dimensional Lie algebras. There's the Lie algebra of vector fields, and there's the Lie algebra of functions with a Poisson bracket. And it turns out they're related. Okay, so let's do this. Okay, so what I want to say. So on M is R2D, or a general symplectic manifold. Okay. What you can do is this: you can take f. If somebody gives you a function, and so I'll say this. I'll just write this. I'm just writing using this notation to say it's a function on M, and I'm not worrying too much about what kinds of functions we're talking about, what their properties are. Okay, then what you can do is you can associate this. You can associate a function, a vector field. And what we're doing here, it's actually a little bit like what happens in regular geometry. If somebody gives you a function, somebody gives you a function, you can compute the gradient, and yeah. So this is an analog. Let me just say this is so what we're going to be doing here is going to be an analog of in the inner product case. So an analog of f goes to f, vector field. Okay. So what you can do in the what you can always do, somebody hands you a function on a space, is you can compute a vector field just by taking the gradient. Okay. So gradients are one kind of vector fields. But if you're on a symplectic manifold, you can take something a little bit different, which is in some senses the symplectic version of the gradient. And then the formula looks like this. So write down the formula. It's the sum into D. It just because it's going to be a vector field, so it's going to have some DDQJs, and then it's going to have some components DDPJ. And then the coefficients are just the F, the PJ minus the F, the QJ. Okay. So there's this kind of analog of the gradient vector field that for any function on a symplectic manifold or on a phase space, there's this vector field X sub F. Okay, and now the and so
invariant on the coordinate chain.
What?
It's got XF invariance on the coordinate chain.
This
like you use another system of Pi prime and Qi prime. Are these two the same?
Yeah, I mean, this expression I've written should transform as a vector. Yeah, so yeah, if you change your coordinate charts, this should yeah, I mean, this should behave. This behaves as a vector field under coordinate changes. That's all. Yeah, yeah. And so yeah, so this makes perfectly good sense on a general manifold. I guess I've written it out with respect to coordinates, but it makes perfect sense on a yeah. I mean, it behaves nicely when you change charts on a manifold. Okay, and then now I guess maybe the thing you should do is you should look at this thing and say, wait a minute, you know, this guy looks a hell of a lot like the formula for the Poisson bracket. So what you could do is you could say that, so xf applied to a function is really just, let's get the sign right, is just this. So if you go back and look at the formula for the Poisson bracket, this is just, yeah, applying this vector field to a function is the same thing as bracketing the function, Poisson bracketing the function with f. Okay. Or another way of saying this, I guess, yeah. So it's i.e. x f of some g is g f. Okay. And so now what this implies here, this fact that this. Now, if you play around a bit, what you see is that so here you actually had a Lie algebra. So this map this is a Lie algebra homomorphism. From functions. So functions on M. Remember that they're a Lie algebra with a Poisson bracket. So this is a Lie algebra, the infinite Lie algebra functions on M with a Poisson bracket, and then this map here is vector fields. Take the vector fields with the so-called the Lie bracket of composition of vector fields. So you can check the, these are both Lie algebras. You've got a map from one Lie algebra to another Lie algebra, and you can check that it preserves the brackets are preserved. And I guess to say that the brackets are preserved is this condition, that xf, that if you take bracket xf and xg, you'll get the vector field you would get from this guy. So this is the homomorphism property from this Lie algebra to this Lie algebra. Okay, now so now there's various interesting things about this map. It's between two differential spaces, which is problematic. But just a couple of technicalities about this is that you can not all vector fields are of this form. That when you take a function to a vector field this way, you don't get all possible vector fields. This is called this guy is called a Hamiltonian vector field. And so saying something is a Hamiltonian vector field means it's a vector field of this form for some function. And one reason for calling it Hamiltonian is that one source of such vector fields is if you pick a Hamiltonian function and then you ask what's the vector field that Hamilton's equations tell you gives you the trajectories that you're going to evolve corresponding to that Hamiltonian. In classical mechanics, well, it's this vector field. It's the vector field for kind of the dynamical evolution corresponding to the Hamiltonian given by F. But then one slight technical. This is not quite. This is close to being an isomorphism between Hamiltonian vector fields and Hamiltonian. So Hamiltonian vector fields and functions are more or less isomorphic vector fields. There's a technicality here that that the constant function here actually goes to 0 here. So the constants here go to the zero vector field here, which causes problems we'll see later on. Okay, so that's the general abstract nonsense about this. Yeah. Okay. Okay. And again, everything. Okay. Again, everything that I've said here, this works. You know, you can write it explicitly. I've written it explicitly in coordinates for R2D, but you can make it work on an arbitrary symplectic manifold. Okay. Okay. Now what we're interested in. So what we're really interested in is this. So. So our interest is Lie group action of a Lie group G on a phase space. So this is actually what we're ultimately trying to go with. So these phase spaces that we're talking about are, characterize some kind of physical system, and we're interested in symmetries of physical systems. So we're interested in cases where there's a Lie group that acts on M. And so examples are going to be, if your phase space is just Q's and P's for some particle, there's going to be translational symmetries are going to act in a way we'll see. Rotations are going to act, and you're going to have more interesting Lie groups acting on the phase space, and it's going to give us and this is what we actually want to study. And I think maybe actually before I get there, I should actually explain kind of a motivation. Is that the standard physics derivation of symmetries. Well, let me say, so the standard physics story that you'll see in every physics textbook. And so I want to kind of explain that I'm doing things intentionally in a different formalism than the usual one the physicists use, because it's different just because, well, partly because it's different to do something different, and partly because this actually is in some ways more powerful. It gives you different some group actions that you really kind of can't see in the usual physics formalism. And so the standard physics story is Noether's theorem. And so what you find is that you have a so in Noether's theorem is done in a different kind of context for studying dynamics, where you, instead of using Hamilton's equations, you set up a Lagrangian, you pick a Lagrangian, and then you look at the Euler-Lagrange equations for that Lagrangian. Okay, and so it's a different approach to mechanics. You can do things either way very often, but if you're doing it in Lagrangian mechanics, so this is Lagrangian mechanics. And so Noether's theorem basically says that if the action of G preserves the Lagrangian in function, you get conserved you get, and maybe it's a good idea to even you get conserved quantities. And so from the Lagrangian point of view, you're going to derive the existence of a momentum function, the existence of an angular momentum function, and and other symmetries, and you're going to derive their conservation laws all in Lagrangian mechanics. So here, what we're going to do is we're here this. So here, it's an alternate path to the same quantities. And you can argue about which is better. I mean, one argument for this alternate path is that this works, is that gives some examples that are not, give some let me say some extra examples. So what's always, what I think is the argument for this is, one argument for this is going to be that you can actually do some things. You can actually get some conserved quantities and some examples of things which are very hard to see in Lagrangian mechanics. But anyway, this is just so if this, I'm trying to make some kind of connection to the standard story in physics, because it's we're aiming towards the same quantities, the same quantity, which these conserved quantities which are associated with symmetries, but we're going to get them by a very different route than you would have seen if you've seen the same thing in a typical physics class these days. Now, if you take a class in Hamiltonian mechanics, though, you'll see some version of what I'm doing here instead. They're probably without as much geometry. Okay, so let's see. So now what the okay. So now the so if we have the action, if a Lie group acts on M, what that means is that we've got for each G and G, you have a map from M to itself that takes M, element of M, to G dot M. So this is what standard thing I've been talking about often about group actions. And now what you want to do is then, but what happens is that that this gives at the Lie algebra. If you look what this is doing infinitesimally, this implies that you're going to have a map L element that it gives you from a Lie algebra element is going to give you a vector field. And if you really want to write a formula for it, it's going to be the vector field. XL is going to be the thing that if you apply it to if you think of vector fields as these first order differential operators, if you apply it to a function, it's going to be the derivative ddt of f at e to the TL acting on it on M at t is equal to 0. So you imagine at each M, you imagine acting with e to the you imagine exponentiating the Lie algebra element, getting a group element acting with M, and then taking the rate of change of this as t goes to 0, and that's going to give you that's going to give you a linear operator on functions, which is going to which tells you what the vector field is. Okay, so that's that. Now, okay, now there's one kind of there's a confusing sign here. So let me. Okay. Let me just say a word about this confusing sign. Remember that I said that your vector field came, with a representation as a Lie algebra representation on functions. But you have to remember that when you that you have if you have a group representation on functions that's induced from the group acting on the underlying space. There's an inverse here. There's an f of G inverse the algebra of M. So in order for this to work out when things are non-commutative, you have to have this inverse here. And that inverse here that gives you a minus sign. And if you take, so then pi prime, now the Lie algebra representation depends on the Lie algebra element. You get by differentiating this thing. And it's d dt, the f of e to the minus t. Okay. And that's so, and what that is that's going to be minus x sub l. That's right. So anyway, you just have to watch out that there's a what you're getting is for elements of Lie algebra, you're getting a vector field here, but you can do it this way and get this vector field. But if you really want this, if you want this to be a Lie algebra homomorphism, you want to think of it you want to think of it this way as coming from this representation, because then these guys automatically give you a Lie algebra homomorphism. So if you want a Lie algebra homomorphism, you have so L goes to minus x of L, where x of L is defined this way, is a Lie algebra homomorphism. In other words, what you got is minus x of L1 minus x of L2 is equal to minus x sub L1 L2. And so here, this is the Lie bracket on the vector field. So it's the Lie bracket over here. And here, it's the Lie bracket on the Lie algebra. But there's anyway, you have to, this minus sign is a source of great confusion about how to deal with it. Okay, so now we finally get to what I want to the main point here. So what we want to do. Okay, so we have, whenever we have a group acting on a phase space, we have a map.
Oh, then I have a question.
Sure.
So when you talk about the functions on M with the Poisson bracket, it's mapping as a Lie algebra homomorphism to a vector field with the Lie bracket, then it's not having a negative sign. So
right.
That's actually Lie algebra homomorphism.
Yeah, no, that's fine because that yeah, they're I mean. That's hard. There's another sign you have to keep track when you do that. But there you've got a. I mean, the problem is coming from this guy here, and this guy here you really only see, when you're dealing with, sorry, there should be an L here. Sorry about that. Okay, so. This minus sign comes about here. You don't have this kind of equation. You don't have this kind of equation and this sign to worry about when in the other case. In the other case, you're defining things based on Poisson brackets, and then there's also a sign problem there, but that just depends. The sign depends upon which order you take the Poisson bracket. So you have to keep track of signs very carefully. And when you're in the homomorphism from functions to vector fields, you have to make sure that you keep the Poisson, that you work with the right direction of the Poisson bracket. But in this case, you have to, the minus sign appears here on this. But anyway, and then you can compare the two, and you have to make sure you've done something consistent. So the minus sign is a pain everywhere, but it appears differently in that case than in this case. Okay. And I think I remember spending far too much time trying to make sure I had all the signs right when I wrote this. So this is one place where I think the signs are correct in the book. Okay. Let's see. Okay, so now what's the the bottom line here. Okay, so what I want to do is I've got, remember that I've got this guy here. It's actually kind of what you were asking about. So you've got so from the group action, each element of the Lie algebra is giving me a vector field. But I've also got so if x sub L is Hamiltonian, modified defined function u sub L such that x sub L is equal to x sub mu sub L. Okay, so here you've got functions goes to vector fields, and you've got and here you've got Lie algebra. And so so here you got L. Anyway, so L goes to minus x sub L. Is that right? Or yeah. And then here you've got something u sub L goes to x sub u sub L. Sorry, again, yeah. This is where this minus sign is tricky. You have to define things correctly there. And I think I've, well, let me just say it here. And so the way I have tried to carefully define things so that these are equal. And when this happens, then you say u sub L is the moment map for the action of G on M. Okay, and so it's these guys that we're going to be interested in. It's these functions that whenever. So the bottom line is we get L element of VG goes to u sub L, a function on phase space. Okay. And these functions, these are going to be your conserved quantities that you've actually gotten, that you also get, that Noether's theorem tells you how to get by a very, very different method. And I'm running out of time, so I can't give they're the examples, but I work out the examples in the textbook of the examples. G is equal to R3 of translations on. So if you have if you have Q's and P's for 3 dimensions, then the translations act by translating the Q's and leaving the P's alone. And if you ask what's the moment map is going to be actually the momentum functions. And then the other example is G is equal to SO3 rotations. If you rotate the Q vector and P vector in the same way, you're going to get an action of SO3 on R6. And you can ask what's the moment map. So, and for each element of the Lie algebra, you're gonna get, so L I is an element of the Lie SO3 is going to go to U sub Li. And this is going to be the angular momentum. So this is worked out somewhat in the book, and it's also part of your problems to look at. But this is, so one of the standard things that you derive using Noether's theorem is to use translation symmetry of Lagrangian to get conservation of the momentum function, and then you use rotation symmetry to derive these angular momentum functions and get conservation of the angular momentum functions. But here we're this is how they appear here. Okay, so then let me then just quickly. So now I'm kind of back to go back to where I was at the end of the last class. Okay. And this is what's in chapter 16. So end of the last class. I was there talking about stuff that's in chapter 16, and what I said there was that quadratic polynomials, so homogeneous quadratic polys are a Lie algebra. They're a sub-Lie algebra of the algebra of all functions, and they're the Lie algebra of something called the symplectic group. And what happens is that if so SP of 2dr is are the linear transformations of M, we'll say here, preserving omega. And then their Lie algebra is the homogeneous quadratic polynomials with this Poisson bracket. And I don't know what. Okay. And then if so, given any group, any Lie group G, preserving, acting on M, preserving omega, then what you have is that G is so G then sits inside the symplectic group. So all of the elements of G correspond to symplectic transformations. And then Lie G is then inside the Lie SP. But remember that, but this is the homogeneous quadratic polynomials, and here L is L goes L under this identification of this Lie algebra and this Lie algebra, L gets identified with U sub L is a certain quadratic. This quadratic poly. Okay. So anyway, so you have a very, very general phenomenon that in some sense what you've done by studying, when I've done by studying these homogeneous quadratic polynomials in the Lie algebra, is that I've kind of created the biggest possible Lie algebra corresponding to Lie groups that act on the phase space, preserving the Poisson bracket structure. And then if you so in any particular case, what you want to do if you have some Lie group action, I know you want to find some U sub L, and this is the moment map. This is This is the moment map. Okay. So in general, for a general Lie group acting on a general manifold, you don't necessarily have, this doesn't necessarily happen. This only happens is acting linearly. If you have a linear action on M preserving this guy, then you have this. Then you get this. Okay, unfortunately, I'm kind of running out of time here. But what's in section 16 point?
What is M here in Euclidean space, a flat space or a manifold?
Sorry, what?
M here a flat space or a manifold?
No, yes. So in this case, yeah. So here M is just R2D. It's So you want to have, because you have, yeah, and then this is just a linear transformation on here. But so the story that I was telling you earlier about groups acting on symplectic manifolds and how to get moment maps, that works on any manifold. And for instance, the functions are not necessarily quadratic functions. Functions can be any complicated function. Here you're talking about linear actions on R2D, and then you're getting quadratic polynomials. But this is okay, but then then we're kind of back where I was at the end, and I really make sure, maybe I'll say a little bit about it next time again to summarize this. But it's if you look in section 16.1, there's very explicit formulas for what these what this Lie algebra looks like in terms of matrices and how it's related to the functions. So if you actually have some Lie group acting in some way by matrices on this guy, then you can figure out you can figure out from those formulas what the mu sub L is going to be. But these are all of this is all about trying to get our hands on these functions that whenever they kind of encode the whole story of how the Lie group is acting on phase space in this so-called Hamiltonian fashion, and then it's these guys. When we go to the quantum theory, it's these guys are going to give us our observables and our conservation laws and everything we want. So there's a little bit. So maybe I may say a little bit more next time to summarize this and finish this. But what we're doing, this is pretty much the end of what I want to say about about the classical story and about phase space and this. So what we're going to do next is actually get back to quantum mechanics. And the thing that we're going to take away from all this is we're going to take away this knowledge of how, if we have a group acting by symmetries in the sense of preserving the Poisson bracket on phase space, we have these very, very interesting functions on phase space, which are our moment map functions for the symmetry. And those are going to, when we quantize, these functions on phase space are going to become operators, and they're going to be kind of the central operators we care about in the quantum theory. Okay, so I guess maybe I better stop it. So any questions right now? Okay, but that's pretty much how that is mostly what I want to say about these chapters 14, 15, and 16. There's a bunch of examples worked out there, which I hope which I haven't had time to work out all the examples I would like. And you should definitely make sure you look at those. And I hope what I've told you today and what you saw before should be enough. Also, you can work out the examples that are in the problems should also help. But okay, questions? Okay, then if not, I'll stop now. But do come back in a few minutes if you want to talk some more about this or about anything else. Okay. Okay, bye. Bye for now.
Thank you.
Bye.